right, Math 5130, starting a new lesson. We're going to get into ANOVA. ANOVA is just the analysis of variance, and it's a really cool procedure developed by Fisher years ago. And what it does is it looks at, it examines the ratio of variances, namely what we call variances between and variances within, to make a statement about the equality of three or more population means. So if we're just comparing mu1 and mu2, we use just an independent samples t-test. But if we have three or more population means, we have to dive into this new statistical technique called ANOVA. Now, the calculations are really complex. I don't think it's appropriate to dive into that for a class of this nature. That's the cool stuff to me, but I don't think it's going to be the cool stuff to you. So one thing I do want to tell you a little bit, to get a little bit mathematical and statistical, the calculation of the p-value depends on what we call the F distribution, not the T distribution. The F distribution behaves a lot like the T distribution in that there's one for each pair of degrees of freedom. So if you have your degrees of freedom like 2, 3 or 2, 4, those distributions will be different. So therefore, the p-values will be different. That's the reason I'm telling you that. But we're lucky. We run our model. We'll have our degrees of freedom for the numerator and denominator given, and the p-value will be calculated using technology. One thing about the F distribution, it's skewed. F values cannot be negative. And again, the shape of the distribution depends on the degrees of freedom. So back when we reported the T distribution, like the results for a independent samples t-test, using a T, we had 1 degree of freedom. And we ran into this with Levine in the previous lesson, where we have 2 degrees of freedom, not 2 as in 2, but the first degree and the second degree, so they're separated by a comma. You'll see, it's pretty simple there. At least that part of it is. So what's needed? We need to look for a dependent variable that's quantitative and an independent variable that's categorical with 3 or more levels. Now, let's look at the data set over to the right. If I was going to look at or examine the HF SCI score, and that's some sort of heart function score. If I'm going to look at that over sex, and you can scan down through there, I just said male and female. So it's a categorical variable, but there's only 2 levels. Well, I'd use a t-test. But if I wanted to examine the mean, the difference in the means across this heart function score across group, you can look down through there and you can just glance and see we have ET and we have usual care and we have ETHC. So we have a categorical variable with more than 2 groups, 3 or more. So therefore we would dive into the ANOVA model. So a research question for this could be, is there a significant difference in means for the heart function score over group? Again, if it was over sex, we would not use ANOVA, we'd use a t-test. So assumptions, we need normal distribution. So in other words, our sample data need to appear to come from distributions that are normally distributed. We have the equal variance assumption, we have the random assumption, and we have that the samples are independent. Independent is just a fancy way of saying that the scores in each group aren't related. Independence is going to be an assumption for most of the tests, not all, but most of the tests that we study. For example, a dependent samples or a matched pairs t-test, which we studied in the last lesson. The samples aren't independent, so that wasn't an assumption, but it is here. So the way plays out is we test our null. So we have, let's say, k-means, where k is 3 or more. So we assume that all the means are equal, state the level of significance, 0.05, just as we've always done. Calculate the test statistic and p-value using technology, just as we've always done. Make a decision, just as we've always done, and then calculate post-hocs if the test is significant. Now, a little bit more about post-hocs. Well, in just a second. So if we have a statistically significant result, that means we have rejected the null. We're assuming that the means aren't equal. So what we can conclude that if our p-value is less than or equal to our alpha, then we conclude at least one pair of the population means is different. So if we're comparing mu1, mu2, and mu3, and we reject the null, then we're concluding that either mu1 and mu2 are different, either mu1 and mu3 are different, or mu2 and mu3 are different, or all of them. So at least one pair is different. If we fail to reject, then we have a result that's not statistically significant. So there's not enough evidence to reject the claim that the means are equal. We kind of land on the statement that we have equal population means, although we really need softer language than that, and just say that we can't reject that claim. So, decision caveat here, let's just say as an example, we're testing the quality of mu1, mu2, and mu3, so we have 3 population means. So essentially we're comparing mu1 and mu2, mu1 and mu3, and mu2 and mu3. So if we reject the null, then at least, could be all of them, but at least one of the pairs is statistically significant and different. More on post-hocs. I'm going to teach you in this class only 2 post-hocs. I'm going to teach you the Tukey HSD, and I'm going to teach you the Bonferroni, but there are others. The Tukey HSD is a little more aggressive. Bonferroni is a little more conservative. It will give just a little higher p-value. Tukey HSD will give a slightly lower p-value under similar conditions. So, if we're comparing mu1, mu2, mu3, and mu4, then as a post hoc, we would compare mu1 and mu2, mu1 and mu3. Again, all the pairwise components for the post hoc. And again, it's important for you to kind of tattoo this to the brain. If, and only if, our test is statistically significant. If the ANOVA test is statistically significant, then we must focus on post hocs. If the test is not statistically significant, if the ANOVA is not statistically significant, then we do not need to report or run post hocs. Now, what are post hocs? You would think that if you're just comparing 2 means, you would just run a bunch of independent samples t-test. Well, you can't do that, because what happens if you do, you inflate the family-wise type 1 error rate. So let's think about it this way. If I know if I compare mu1 and mu2, I'm allowing myself a 0.05 error rate, and then I make another comparison at a 0.05 and another comparison at a 0.05. That type 1 error rate family-wise for all collectively, in this case of the 6 comparisons, will inflate. Now, if that doesn't make any sense to you in terms of like a probability perspective, that's fine. Just tattoo it to the brain that if we did just a standard t-test, and not one of these special types of t-tests like Bonferroni and Tukey HSD, then we are not controlling for that probability increase. So long story short, just do it. So just to give you an illustration, as we increase the number of pairwise tests, our family-wise type 1 error rate increases. So a pretty good estimate is 1 minus alpha raised to the nth power. So at 0.05, if we do one comparison, then we're going to make a type 1 error rate about 5% of the time. If we do 2 comparisons, then about 10% of the time. But if we do 6 comparisons all the way at the bottom, you can see that we're inflating that type 1 error rate to about committing a type 1 error about a fourth of the time. That's just too much. So some really, really smart people named Tukey and Bonferroni came in and came up with these procedures to control for that. All right, gang, I think that's it. Now there's one more thing. If you're interested in the calculations, you can reach out and I can share a video with you that I've created for one of my master's level statistics classes for people pursuing masters in mathematics. But you can see that we have these sources of variation. We have a between variation and a within variation, and our F statistic is just the ratio of those variations. And we get into something called the mean square between and mean square error, and that's just the sum of squares divided by their degrees of freedom, their respective degrees of freedom. If this is something you just want to completely ignore, if you're kind of looking at that like the guy at the bottom, you're like, what the heck? That's fine. You don't need that. Again, these calculations will be made using technology. All right, gang, that's all I got. Take care.